Please allow me to introduce our next speaker, Dr. Hugh Ross. Astrophysicist Hugh Ross, founder, senior scholar, and former president of Reasons to Believe, holds a degree in physics from the University of British Columbia and a PhD in astronomy from the University of Toronto, Canada. His books include Why the Universe is the Way It Is, Improbable Planet, and Design to the Core. Hugh has spoken at hundreds of universities, conferences, and churches around the world. Please enjoy Dr. Hugh Ross's presentation.
And I'm the oldest astronomer speaking here at our workshop, and this really does strike me as deja vu all over again, because I'd been studying astronomy since I was 7, and it was during my teenage years when they discovered the first quasars. And this is a photo, a Hubble Space Telescope photo of 3C273, the first identified quasar, identified by Martin Schmidt and Beverly Oak back in 1963. It's optically the brightest quasar. It's even visible in a small telescope. In fact, when it was discovered, I got out my 4¼ inch telescope and actually was able to see it through my telescope. And you know my story. It was Big Bang cosmology. It was a major factor in my becoming a Christian in a neighborhood where there were no Christians. But I remember when they were discovering the first handful of quasars, the comments we were seeing from both astronomers and especially from non-astronomers is that these quasars were too bright, they were varying much too rapidly in their brightness, they were too distant, and there's only too few of them. This can't fit the Big Bang creation model. Because what we're seeing is, if we actually recognize them as being at cosmological distances, they're thousands of times brighter than our galaxy, but they're the size of our star. I remember I had Jeffrey Burbidge as a professor when I was at the University of Toronto, and he was adamant that because of these features of quasars, that the quasars are actually proving that the Big Bang model was wrong, saying they're too bright, they're varying too much, and we think we must be wrong on the distances. They can't be as distant as they are. So the Big Bang was under challenge. However, the first quasars to be discovered were, of course, the brightest quasars. And I remember back in those days they were saying, we're only finding a handful of these quasars. Nobody had any hope that we would find more than 50. And what do we have? We know there's at least 1 million quasars. There might be as many as 3 million quasars. And yes, most of the quasars are quite faint. But of course, the first ones you're going to discover are the brightest ones. The first ones you're going to discover are the ones that are the most variable in their brightness. Those are the ones that are going to be easy to detect. And so here we are with the James Webb Space Telescope. It's got a 30, hopefully a 40-year mission, and we've only been in it for the first 2 years. And so we shouldn't be surprised that we're seeing deja vu all over again. We're seeing the brightest ones show up. And it does seem to be challenging a lot of our ideas about the Big Bang. It's deja vu for another reason, because my PhD thesis is sitting right in front of here. It's 2 volumes. I originally told my thesis supervisor it's going to be 4 volumes. He said, no, that can't be. That's not allowed. So I wound up putting it into tiny print, but 850 pages. And people say, why did you make your thesis so thick? It says, I knew my results would be challenged. And so I knew I had to actually put the data in there for my examining committee to see it. Now, my PhD thesis was on flat radio spectrum quasars. And, when you look at galaxies, the spectrum is very steep. So this is typically what we expect for radio galaxies. But I had this idea that these steep spectrum radio sources were galaxies that had something weird going on in the cores of those galaxies. But I noticed that none of the astronomers on my committee actually thought that that was true. They said, no, there's no way that these are associated with galaxies. But what I noticed is that for the steep spectrum radio galaxies, if the spectrum was less steep, it was more difficult to see the galaxy. So I thought, well, maybe this just progresses all the way to the flat spectrum radio sources. And at that time, the best optical images we had of the universe were those that were done by the Palomar Sky Survey. And, I heard that Roger Windhorst was at the Santa Barbara observatories, which is here in Pasadena, and they had a set of the Palomar plates. The only other institution that had a set was the University of Toronto. So I actually had access to those plates. And so I went through those plates trying to find galaxies associated with my flat spectrum radio sources. I'm going to show you the 4 best examples I found. Now, these were photographs of what was on the plates. When I actually looked at the original plates with a magnifying glass, there were 4 out of the 108 sources I was looking at where I thought I could see very faint wisps of what looked like a galaxy. Here are the examples I show here. And I remember when I defended my thesis, the astronomers just said, this is not, you have to use your imagination to think there are galaxies there. And I said, well, there will be telescopes coming in the future that will actually be able to show this. And yes, we can't see it now, but I said, the fact that there seems to be even a hint, isn't this suggestive? Well, that didn't go over very well. The other thing that didn't go over very well is they said, your observations seem to be of too high of a quality. And therefore, we think that you're really not seeing these radio sources as they are. And the fact is, I discovered 8 new steep spectrum radio sources. And they said, well, if you're adding 8, that brings up your list to 113. And that seems to be too many, because people were thinking these quasars were not very abundant. And so the fact that I had found 8, they said that can't possibly be. And I remember there was one astrophysicist there who prided himself in his observations and said, I can't believe your data is of higher quality than mine. And I said, well, I did my observations when it was 40 below. And when it's 40 below, all the water comes out of the atmosphere. And you get much higher quality observations. And also I was doing my radio scans at 4 times the speed of other astronomers. That reduced the signal, the noise by about a factor of 2. But that's one reason why it took 6.5 hours for me to defend my thesis. Because they were basically looking at the data very carefully, going through, every one of them had a copy of the thesis, and they were going through and saying, okay, is it really of this quality? What really threw them as I was seeing structure. How can a quasar have any structure? We all know that they're a star-like. And what was not known at that time is that when you were hearing David Bloch talking about merging galaxies, sometimes when galaxies merge close together, each one of them has got a quasar in it. And so, yes, I'd be observing a source and I'd say, hey, there seems to be some width to it. Well, nobody really knew about how galaxies merged together back at that time. Nobody knew that the energy, because I was trying to explain the energy. Saying, I agree, synchrotron radiation doesn't explain the intense energy that's coming out of this. And I was saying, well, maybe there's an inverse Compton effect that might give enough energy. But I remember people saying, hey, even if you go there, you can't explain the energy. So yeah, my thesis defense ran on for 6.5 hours. In fact, one of the professors said, maybe we need to bring lunch and dinner into this defense. But finally they told me to leave the room. And so I waited 110 minutes while they were deliberating about whether I would get the PhD or not. And finally they called me back in and said, you're going to get the PhD. But what was interesting, when I showed up at Caltech to do postdoctoral research, Chip Arp noticed, hey, you're finding these new sources? And I kind of laid a hint with them. Some of these quasars I'm seeing, flat radio spectrum radio sources, are right next to galaxies that are relatively close. And I actually cheated because I knew that was his big interest. He thought these quasars were being blown out of the center of these galaxies, but I wanted redshifts. And so he took redshifts for me. Wasn't too happy with the redshifts he got because they're all greater than 0.2. But that kind of told me that's why I'm not seeing the galaxies. These sources I'm looking at are far away, more than 2 billion light years away. That's why we're not able to see the galaxies. Well, what's happened since then, we now have the technology where we can use a big telescope and we block out the light of the quasar. And so, for example, this is a new image of 3C273, where they purposely block out the light of the quasar, and then they can see the galaxy that surrounds that quasar. Notice, however, that the blocking feature doesn't give you a lot of details of the galaxy, but it does demonstrate that a galaxy is there. And again, I mentioned, today we know there's not just 50 quasars, there's actually maybe 1 to 3 million such quasars. And also something we know today, what's powering the quasars is not synchrotron radiation or inverse Compton radiation, it's supermassive black holes. I also remember we had Kip Thorne as a professor when I was at the University of Toronto, and he was talking about how with a black hole, you can get matter converted into energy with 8 or 9% efficiency. Well, we now know if you get the quasar rotating very rapidly, you can get 42% efficiency. So today we understand how we can have objects that bright and that tiny and that far away and not violate Big Bang cosmology and not violate any physics. We don't need new physics to make that all work. Well, the James Webb. Does the James Webb Space Telescope actually challenge a Big Bang cosmology? Well, again, what we're seeing is deja vu all over again. They're basically saying the galaxies that we're seeing in the first billion years of the, and that's what's called the cosmic dawn. It's basically going from the cosmic creation event to when the universe is 1 billion years old. They're saying these galaxies are too bright. They're too numerous. We're finding too many of them. The supermassive black holes within these galaxies appear way too soon in the history of the universe, and they're much, much too massive. And so far, no metal-free stars have been detected, because that's a fundamental prediction of Big Bang cosmology, that the universe begins with nothing but hydrogen, just protons and electrons and neutrons, and hydrogen's a single proton with electron going around it. And during the first 4 minutes after the cosmic creation event, the universe is going from a near infinitely hot temperature, and it cools down, and there's about a 20-second window when it passes through the temperature range where nuclear fusion can occur, and that's when 25% of the hydrogen by mass gets converted into helium. Then you get a trace amount of lithium. And somebody was asking me at the table, well, what's the trace amount? Well, it's 1/100th of a millionth of the amount of hydrogen. So it really is a trace amount. It's almost entirely hydrogen and helium. But one of the missions of the James Webb Space Telescope, can we actually prove that there was a time in the history of the universe where all we see is hydrogen and helium, a trace amount of lithium, and nothing else at all? Well, this idea, has the Big Bang model been challenged? Well, again, I'm old enough to remember when the Big Bang creation model had competition, where there were people promoting the idea of a steady-state universe, or the quasi-steady-state universe that Jeffrey Burbidge was so fond of, or the idea that it was an oscillating universe, the reincarnating universe of Hindu theology, or the hesitation universe. But what we've been noticing over the past 100 years is that we've gone from the recognition that the universe seems to indicate that the universe has expanded from a small volume to the idea that it not only has expanded from a small volume, the beginning was hot, not cold. We eliminated the cold Big Bang model to a hot Big Bang model. Then we recognized through the space-time theorems, it's not just a beginning of matter and energy, it's a beginning of space and time itself. And then I remember back in the 1970s, they were saying the evidence is strongly supporting the fact that it's a flat geometry, hot Big Bang universe. And then in the 80s, that there's actually an early inflation event where the universe expands from the cosmic creation event in an extremely brief moment, about 10 to the minus 34 seconds in duration. We got the universe expanding millions of times faster than the velocity of light. then it goes back to its normal expansion, to where today what we see is a Big Bang model referred to as the lambda CDM model, where lambda, the Greek symbol, refers to dark energy, where the universe is mostly dark energy, and then the second dominant component of the universe would be cold dark matter. So what I want you to notice here is that as we've been learning more and more about the universe, is that we've gone from a very broad description of a Big Bang universe to a more specific and a more detailed and a more narrow description of what kind of Big Bang model we're dealing with. And so the mission, one of the primary missions of the James Webb Space Telescope, can we actually more narrowly define the range of viable lambda CDM models? And so there's a consensus now that we do live in a universe that is a Big Bang universe where most of the stuff is dark energy, and then secondarily cold dark matter. But if you look at the lambda CDM models that are in the scientific literature today, we see that we're not dealing with just one lambda CDM model, but several dozen distinct kinds of lambda CDM models. So for example, there are lambda CDM models where they say, well, maybe not all the dark matter is cold. Maybe a small percentage is warm. And so the question is, well, how warm would it be and what kind of percentage are we talking about? Is it less than 1% or is it a few percent? And then we've also got telescopes at the South Pole that are trying to determine, well, we seem to have a case that it's an inflationary hot Big Bang model. The evidence is very strong that that's the case. But maybe we could actually investigate what kind of inflation took place in the first 10 to the minus 33 seconds after the cosmic creation event. Then dark energy. Is it governed by a single constant or multiple constants? And so we're now trying to explore that. And what about the different kinds of dark matter? What are the different kinds of dark matter particles? But where I think the James Webb really has some potential, what about these population 3 stars that you heard Jeff talk about in the previous lecture? These stars that form with just hydrogen and helium and then give birth to the second and third generation stars. What are the masses of these firstborn stars? What are the population levels? Are they all very massive, or do you have some that are low mass, some medium mass, and some high mass? And what are the numbers? What are the densities of these population 3 stars? And so what I want to share with you is just a little bit about what James Webb has discovered so far about these population 3 stars, again, stars that form with only hydrogen and helium and nothing else. So before any other elements are fused inside the stars. And so what we notice today is that there's so much gas and dust in the universe, and the universe is cooled down so much from the cosmic creation event that you can't have a star forming that's more than 150 times the mass of our star, the sun. So that's the limit. But what astronomers have recognized for a few decades is that if you don't have these heavy elements heavier than helium, and what we refer to as metals. You got to remember, when astronomers talk about a metal, they mean anything that's more heavy than hydrogen and helium. So all the rest of the stuff in the periodic table they call a metal. But that the lack of those metals and the high cosmic temperature, the fact that the radiation from the cosmic creation event was much warmer in the first billion years than it is today, that would actually allow stars more massive than 150 times the mass of our star, the sun, to form. But there's still a huge debate. How massive can stars form where you don't have metals and where you've got a relatively high temperature of the cosmic background radiation? Is the limit 200 times the mass of our star, the sun? Is it 300? Is it 500? Is it 1,000? Is it 10,000? So that's one of the missions of the James Webb Space Telescope, to see if that is the case. Now, keep in mind this, in terms of these early galaxies seeming to be too bright. Okay, the brightness of a star goes up with a 3.9 power of its mass, so very roughly the 4th power of its mass, which means if you've got a star 1,000 times more massive than our star, the sun, it will burn 1 trillion times brighter. So yeah, if you just got a handful of these really massive stars, that could explain why some of these early galaxies are so exceptionally bright. You don't need a lot of stars to get a very high brightness, given that the brightness goes up by the fourth power of the mass, if indeed you got stars that are that massive. So these early galaxies, one of the things that came out a couple of months ago is a paper saying it seems like these early galaxies don't have enough elements heavier than hydrogen and helium. Because if you got big stars forming, they burn up quickly. By the way, the speed with which a star burns up goes up with the fourth power of its mass. And so it's actually possible if you got a star, say 300 times the mass of our star, the sun, it burns through all of its nuclear fuel under 1 million years. And when it ends up, it explodes and basically showers interstellar space with the ashes of its nuclear burning. So you'd expect, if indeed there are lots of these big massive stars, that the abundance of elements hydrogen, heavier than hydrogen and helium, would quickly get quite high. But as we make the spectral measurements of these early galaxies, and galaxies that come in at about 470 to 770 million years after the cosmic creation event, it seems like the abundance of metals is 4 times too low. So this is recognized as a challenge to our understanding of the Big Bang. What we now recognize is that stars forming during the first billion years after the cosmic creation event are subject to a lot of infall of pristine gas. Keep in mind that with an expanding universe, during the early history of the universe is more compact. And so the density of gas is greater. And this is gas that's just hydrogen and helium. That's what we refer to as pristine gas. Has not yet formed any stars. And so these stars that are forming, they're basically collapsing under these gas clouds through gravity, but at the same time they're pulling in all this pristine gas. And if they're pulling in efficiently a lot of this pristine gas, that would explain why the metal abundances we're seeing in these early galaxies is actually much lower than what we'd expect. Because today, when stars form, they're not pulling in any pristine gas at all. But back then, there would be a lot of pristine gas, which would dilute the anticipated metallicity of these stars. Well, one you've probably heard of is that it seems like these early galaxies are way too bright. And so we're seeing galaxies 300 to 700 million years after the Big Bang creation event. And the most stunning challenge to Big Bang cosmology, it seemed like at ultraviolet wavelengths. Now keep in mind, James Webb is basically taking infrared, but hey, the farther away you go, the more redshifted these are. So when they talk about ultraviolet luminosities, they're basically taking out the redshift effect. But it seemed like the ultraviolet luminosities were 10 times too high for our understanding of the range of Big Bang creation models we're looking at. But I remember reading the paper, and number one, they said that these are not actual galaxies we can count on, they're candidate galaxies. So I thought, well, a lot of them might prove not to be galaxies that actually exist during the cosmic dawn. We had Roger here making the comment that we haven't got accurate redshifts of all these galaxies yet. So it appears that they might be existing during the cosmic dawn, but we don't know that for sure. Undoubtedly, though, at least a large number of these 90 candidate galaxies are indeed real cosmic dawn galaxies. But as I read the paper, what I noticed is they were making the assumption that during the first billion years after the cosmic creation event, star formation occurs at a steady rate throughout that billion years. And one of the comments towards the end of the paper is, well, when we look at galaxies from, say, 2 billion years after the cosmic creation event to the present day, with the 13.8 billion year old universe, we don't see that the star formation rate is constant throughout that time. It's stochastic, which means there are periods when you get very aggressive star formation, then not much star formation at all, then another period of very aggressive star formation. So they said, well, let's just assume that what's happening in the first billion years is the same as what's happening in the subsequent 13 billion years. And what they discovered is they put in the model stochastic star formation, they got ultraviolet brightnesses that were 10 times higher than if you assume that the star formation rate was constant. So that seemed to settle that challenge that these galaxies were indeed too bright. And then they found this galaxy called GNZ11. By the way, you got to love the names that astronomers put on these galaxies. Reads kind of like license plates. But this is a James Webb Space Telescope image. So down the bottom right there, they actually blow up. And there you get to see GNZ11, kind of a faint galaxy next to a bright galaxy just above it. But one of the things they noticed about GNZ11, it shows up just 410 million years after the Big Bang creation event. It's a very small galaxy in terms of its size, but with an extremely bright core. How bright is the core? 20 trillion times the brightness of the sun. So a very bright core, very small core. But on that basis, they concluded that these first stars have to be at the high mass end. In fact, the authors of the paper were saying at least 100 times the mass of our star, the sun, but we believe that most likely they're at 1,000 times the mass of our star, the sun, and some of them may be even more than 1,000 times the mass of our star, the sun. This is significant because some of the lambda CDM Big Bang models actually state that there aren't going to be any stars more massive than 200 times the mass of our sun. So it's just some of the data, and there are other papers basically supporting this claim that at least a significant population of these firstborn stars are much more massive than 200 times the mass of our star, the sun. And again, if it's 1,000 times per massive, that's going to mean a single star will have the brightness of 1 trillion times that of the sun. So we only need 20 stars to get up to 20 trillion. But the authors of the paper said that we think there's actually a gradation. Some that are low mass, some that are medium mass, some high mass, and some very high mass. That explains what's going on. And also they made the point that we don't think the brightness can be explained by a supermassive black hole in the center of GNZ11 pulling in gas, and that explained the brightness. They concluded that most of the brightness, in fact, must come from the stars. And partly because they're able to measure the mass of a supermassive black hole, it came in at 2 million times the mass of our star, the sun. And a black hole is not considered supermassive unless it has 1 million times the mass of our star, the sun. Now, our Milky Way galaxy is famous for having the tiniest supermassive black hole of any big galaxy. It's 4 million times the mass of our star, the sun. But at 2 million, they were basically saying the black hole cannot explain the brightness by itself. Most of the brightness must be coming from these stars. And if that's the case, a significant number of these stars have to be more than 500 times the mass of our star, the sun. But the most exciting thing about the research on GNZ11 is they actually found a pocket of gas in the halo of GNZ11. And because of how bright these stars were, those stars actually ionized the gas in that halo. So they were able to measure the composition of the elements in that halo. And here's the exciting thing. All they found was hydrogen and helium, nothing else. So this affirms a major prediction of these Big Bang creation models that indeed the universe begins with just hydrogen and helium and nothing else except for a trace amount of lithium. And so the halo was brightly illuminated by the core stars sufficiently to ionize that halo, that pocket of gas in the halo, and basically showed there were no metals in that halo. So it's the first evidence of the pristine gas predicted by all Big Bang creation models. Now, as Jeff pointed out, there was another research study that was performed that independently affirmed the statement that indeed, during the cosmic dawn, there are stars and gas clouds that are pristine with only hydrogen and helium. In fact, Jeff and I did a Stars, Cells, and God podcast that we recorded just this past Wednesday. I think next Wednesday it's going to be posted, and so you can see the details on that particular discovery. But the most distant confirmed galaxy has been found as Jade's GSZ14-0. And again, you got to love the names that come up with these things, right? But this one is just 280 million years after the Big Bang creation event. Now, this is the earliest confirmed galaxy that they have found yet. And most Big Bang creation models say you're going to get the first stars forming when the universe is about 170 to 200 million years old. Well, this is just a few tens of millions of years after the first time the stars can possibly form. And also they noted that the size of this galaxy is quite small. The half-light diameter, that's the place where you go from peak brightness to half the brightness. That diameter is a little more than 1,600 light years. They calculated that the stellar mass, the mass of stars in this galaxy, had to be 400 million times the mass of our star, the sun. And again, this particular discovery favors that we're probably looking at the first stars forming 180 to 190 million years after the cosmic creation event. And again, they were able to conclude that most of the brightness had to come from stars, not from a supermassive black hole. And I thought you'd be interested in actually seeing an image of one of these distant galaxies. This was actually taken by the Sloan Digital Sky Survey. It's that little tiny red dot that you see there by the arrow. But that is one of these early cosmic dawn galaxies with the very colorful name J1120 plus 0641. But I think the biggest challenge that's been put forward with these new observations from the James Webb Space Telescope has been the supermassive black holes they're finding. And so, for example, with J1120 plus 0641, we're seeing it just 760 million years after the cosmic creation event, but it has the astounding mass of 1.5 billion solar masses. And it's not alone. They found two others that came in the neighborhood of 1 billion solar masses. Now keep in mind the biggest supermassive black holes are ones we see in the centers of gigantic galaxies that come in as high as 6, 7. One comes in at almost 10 times, a billion times the mass of our star, the sun. But these are galaxies we're seeing close to the present time. How can you possibly get supermassive black holes weighing 1 billion times the mass of our star, the sun, showing up so incredibly early in the history of the universe? As I mentioned, there are two others, J1342 plus 0928, just 700 million years after the cosmic creation event, just a little less than 1 billion times the mass of the sun. 690 million years after the cosmic creation event, we got one at 1.6 billion. Now, they have found 4 so far. GNZ11, as I mentioned, is 2 million times the mass of our star, the sun. But notice we're seeing it 410 million years after the cosmic creation event. So one of the questions astronomers is asking today, okay, once you get to 700 million years after the cosmic creation event, you actually get supermassive black holes 1 billion times the mass of our star, the sun. But the most massive one we found at 400 million years is only 2 million. Is there something that happens where you get very aggressive growth of these supermassive black holes once you get past 500,000 or 500 million years after the cosmic creation event? And what is responsible for making these black holes so big and so early? Now, keep in mind we're dealing with a database of 4. It's always wise not to draw too strong of a conclusion when you got a database of just 4. Just like deja vu when I was a teenager, trying to draw conclusions about quasars when you only have discovered 20 of them. That's too small of a database. And again, what I'll be saying here, let's be patient. Let's let the James Webb Space Telescope do its work, and we get up to, say, 300 supermassive black holes in the first billion years. Then maybe we can discuss which of these different Big Bang creation models is actually the model that fits what we see. But the 3 suggestions that have been put out there to explain how we can get supermassive black holes 1 billion times the mass of our star, the sun, showing up so incredibly early in the history of the universe? Number one, again, we know that the gas is denser, and so it's possible that these black holes are very aggressively accreting this pristine gas into the black hole. Black holes are hungry. They tend to suck anything that's within its vicinity into it. Maybe that explains it. Or hey, we really are looking at a large population of stars that are 500, 1,000, maybe 1,200 times the mass of our star, the sun. And if they're all forming in a dense cluster, they're going to burn up quickly, just in hundreds of thousands of years. And when that happens, they become a black hole. And if they're all jammed closely together, maybe these black holes merge. And that's how we get these really big supermassive black holes happening early in the universe. And then there's a number of papers published by saying, if we're talking about a gas cloud collapsing under its own gravity, that's more than 10,000 times the mass of our star, the sun, that's going to collapse and become a black hole without ever becoming a star. In other words, you're not going to see a star. It's going to go from dark gas to a dark black hole all by itself. And now one of the questions is, well, when does that happen? Does that happen at 20,000 times the mass of our star, the sun? One paper said 36,000. Another is saying maybe we can even get it down close to 10,000. But this is interesting, how you can get these really big gas clouds condensing under their own gravity and going straight to the black hole without ever becoming a star. And they would do that very quickly. And so the question is, well, which one of these mechanisms explains how we get so many of these black holes happening too early? And again, my advice is be patient. Let the James Webb do its work, because we're working with a database of 4. But if you want me to make a bold prediction, I would predict that's most likely a combination of all 3 that explains how we get these black holes. But don't hold me to that, because after all, we're looking at a database of 4 of these supermassive black holes. And so once we get up to a database of 100, 200, 300, 1,000, then I think we can make a conclusion about what we're really seeing. And last of all, realize this is deja vu. The James Webb Space Telescope is going to find the bright stuff first. It's going to take a while before we see the faint stuff. And just like with the quasars that we discovered in the 1960s, it took finding the faint quasars to really determine the nature of these quasars. Likewise, it's going to take the discovery by the James Webb Space Telescope of these faint galaxies and calculating, well, what is the ratio of small faint galaxies to big bright galaxies? But again, here's what I would predict, that when we get James Webb Space Telescope taking these very long exposure images, as long as the longest ones that have been taken by the Hubble Space Telescope, this will actually tell us the ratio of faint galaxies to bright galaxies during the cosmic dawn. That will tell us which of these several dozen lambda CDM Big Bang models is on the right track. And what is the ratio of the population of high mass population 3 stars to small mass population 3 stars? We actually see some polluted small mass population 3 stars in the halo of our galaxy. So we do know it's going to be a spread from small mass to high mass, but what are the number ratios of the high to small mass stars? And can we use a James Webb to reveal more pristine gas clouds in the halos of these galaxies? That's going to really tell us a lot about what kind of Big Bang model we're looking at. And it'd be great to actually come up with a date for when the first stars form. Right now, we're saying somewhere between 170 to 220 million years after the cosmic creation event. But if we can nail down more accurately that date, that'll tell us which Big Bang creation model we're looking at. And here's a long shot. Maybe we can actually detect the primordial lithium, that trace amount of lithium that was formed in the first 4 minutes of the Big Bang creation event. That's a long shot because after all, we know the abundance level is around 100 millionth of the abundance of hydrogen. But the answers will come if we're patient. Keep in mind, it took a long time, decades, to get all the answers we wanted from the Hubble Space Telescope. The same thing's going to be true of the James Webb Space Telescope. But let me finish with a brief word about LUSEE-Night. Probably haven't heard of that experiment, but next year they're going to put 4 radio telescopes on the backside of the moon. The wonderful thing about that, we're going to be able to do very long wavelength radio observations. And that can't be done from the Earth. And it can't be done with satellites orbiting the Earth because there's just so much radio noise pollution coming out from human activity. But the backside of the moon is the place that's protected from radio interference on the surface of the Earth. And also it's a place that's unaffected by the ionosphere of the Earth. And so yes, they're looking at putting a radio interferometer on the moon's far side. And for the first time, astronomers are going to open up a new window in the electromagnetic spectrum. That window, wavelengths between 6 and 3,000 meters. And what's exciting about that, that's actually going to give us insight into the Dark Ages, which we heard from both David Block and Jeff Zwerig. That period between 385,000 years after the cosmic creation event and when the first stars form. So when you go from one ionization to the second ionization. LUSEE will be the only instrument in the possession of humanity that will have facility to actually explore what we refer to as those dark ages. And that will reveal how non-luminous matter, non-luminous gas condenses to form stars. So that's going to complement what's being discovered by the James Webb Space Telescope. And about a month ago, we interviewed Brian Keating. He's an astronomer at the University of California, San Diego, and he's involved in the latest research of looking at the radiation from the cosmic creation event, what's happening during the first 385,000 years. And we did that because the message we want to communicate to you in this workshop is, it's not just the James Webb Space Telescope. There are multiple instruments that are going to give us insight on what's going on from the cosmic creation event at 0 seconds all the way up to the first billion years, and then be able to link that, what we know from a billion years, up to the present time today. Bottom line, the more we learn about the universe, the more evidence we gain for the biblically predicted Big Bang creation model. And as I tell people, 100% of the observations sustains the model that was predicted in the Bible thousands of years ago. Now don't get me wrong, the Bible doesn't give us all the details about the Big Bang, but it does tell us the universe has a beginning. It also tells us it's a beginning that includes the beginning of space and time. It's a universe that's governed by laws of physics that don't change, where one of those laws is a pervasive law of decay, which means the universe is going to get cooler and cooler as it continues to expand. Then there are 11 passages in the Bible that talk about the stretching out or the expansion of the universe. This is a huge factor in my becoming a follower of Jesus Christ. During my teenage years, recognizing that only the Bible amongst the world's holy books got the cosmology correct and actually predicted thousands of years ahead of time features of the universe that astronomers were discovering just in my lifetime. And again, the more we learn about the universe, the more evidence we accrue that what the Bible stated thousands of years ago is right on target. Thank you.